My name is Jason Meintjes. I'm a second-year master's student at the San Francisco State University studying mathematics. Today, I'd like to give you a glimpse into our research to give you the main ideas without overwhelming with technical definitions. So, I studied the moduli space of curves. I'd best tell you what a curve is. This is perhaps best illustrated with an example. Here we have a 2 donut hole curve with 6 marked points or punctures. The question is, how can we classify all possible such curves with certain characteristics? So first, a bit of motivation. Moduli spaces are of great importance in diverse areas of mathematics, as well as in theoretical physics. Physicists care about these for applications to string theory, where the fundamental objects are tiny one-dimensional vibrating strings. If we let time evolve, a string can trace out a path or a surface through space-time. Some sort of interaction may cause a branching off and then later a recombination, and this will form that donut hole that we saw earlier. If we let time run infinitely backwards and forwards, as we can do in mathematics, then the branches at the ends become the punctures that we spoke of. So we collect all of these curves in a gigantic set, and we classify them according to some shared characteristics: number of holes, number of marked points. In essence, a great big map, which tells us exactly which curves are in the set, as well as how close one is to another. The original construction of M0n bar due to Knudsen is an opaque procedure involving an unspecified number of what are called algebraic blowups, making it prohibitive to compute all but the smallest example. Construction due to Kranot is explicit, but requires a large number of blowups in increasing order of dimension along all projective subspaces spanned by certain subsets of n-1 generic points. As you can imagine, this too becomes very complicated very quickly and results in a projective embedding with extremely high ambient space. So we end up with what feels like a small object in a very large space. Recently, Gillespie, Griffin, and Levinson proved a conjecture of Mohn and Rana regarding explicit equations which define our moduli spaces, which are given by all the 2x2 minors of certain matrices. In particular, the Mohn and Rana equations give an embedding of M06 bar with codimension 3, as opposed to the codimension 284 given by the Kranot construction. Our work is to compare the 3 constructions for M0n bar for small n, and to use various aspects of each to illuminate more about the spaces of interest. I'd like to thank the ARCS Foundation for their generous support, for allowing me to continue my studies without having to take on extra work. And I'd like to thank Dr. Emily Clader and the San Francisco State University Mathematics Department for all of their support and guidance. Thank you.